Thanks, Becca. Thanks everyone for joining. As Becca mentioned, this is the last session of our winter webinar series, and it's probably the most anticipated one. I know I'm really looking forward to it, and all of the presenters are really looking forward to providing more outreach on this type of work that we do. All of the presentations are really going to build on each other, so that's something to keep in mind with the Q&A. The first presentation will be given by Nathan DePriest. He's a water resources engineer here at WRI, and he's going to be presenting on the watershed scale restoration approach. And then he'll be followed by Greg Phillips, who's going to present on TNT specifically. And last will be Eliza Siefert, who will present on rare earth element and critical material extraction from AMD. So Nate, if you are ready to get started, I'll turn things over to you. Thanks.
Thanks. Good morning. First, I wanted to thank everyone who took the time to attend today. We're excited to share some of the current and ongoing work we're conducting here at WRI. My name is Nate DePriest. I'm a water resources engineer at WRI. I've been here since 2023, where I assist in all things engineering related to our research projects. I've had several years of consulting experience in environmental permitting and design, and I also have my PhD in civil engineering from WVU. My research focused on reclamation of coal surface mines. Today, I'll be presenting on watershed-scale restoration, which is a recent research focus here at WRI. The presentation will be broken into three major sections. First, I'd like to provide some background info on the watershed-scale restoration approach, what it is, what the objective is, and what challenges and benefits present themselves. Next, I'll provide some basics on a case study in watershed-scale restoration in the Muddy Creek watershed. Greg Phillips from DEP will be giving a much more detailed presentation on that case study after me. And then finally, I'll talk about some of our current efforts here at WRI with respect to watershed-scale restoration. So we'll start first with talking generally about the watershed-scale restoration approach. One thing we always like to note before discussing water treatment and approaches to restoration is the Clean Water Act. I think it's useful to remind everyone the overall objective of the CWA, and that is to, quote, restore and maintain the chemical, physical, and biological integrity of the nation's waters. So when we're discussing watershed scale restoration, please keep in mind this is the ultimate goal that we're trying to meet. One other specific thing about the Clean Water Act that'll be relevant today is the permitting structure. So actively managed discharges require NPDES permits, which is important. Up front, I'd like to discuss some impediments to watershed restoration, regardless of what the restoration approach is. From a jurisdictional perspective, time is a fundamental issue, whether we're dealing with discharges associated with operations before or after passage of the Surface Mining Control and Reclamation Act, or SMCRA, in 1977. So discharges prior to SMCRA are referred to as free law, Title IV, or specifically in West Virginia, abandoned mine lands, or AML. Discharges from after SMCRA are referred to as post-law, Title V, or specifically in West Virginia, Special Rec, or SR. There's also NPDES permits for active operations, and that's the current regulatory focus. Jurisdictional things raise questions related to site prioritization and funding. From the regulatory perspective, let's see, the permitting approach is key. So the existing permitting structure of NPDES, which covers point sources, a special rec and active operations, but not AMLs, and then alternative permitting structures like TMDL or water quality variances. Ultimately, we want to do what's best for the watershed, but that may justify looking at, or that may require justifying alternative approaches. So to discuss the watershed scale restoration approach, first we have to focus on individual restoration techniques. So first, I'd like to discuss the point source approach. So this is the existing NPDES permitting structure. So from left to right, I've identified some causes, intermediate effects, and ultimate outcomes. So a key shortfall of the NPDES approach is that the permits may not account for enough of the pollutant load in a watershed. So this results in putting treated individual discharges into a stream that's ultimately dead. See, factors related to the short-term nature of permitted storage can result in no long-term infrastructure for treatment left behind and a permit liability that falls to the state. So in addition to not meeting the CWA, this also results in the state having to build long-term treatment facilities. And then finally, declining coal production over time means less money in the state's bond pool and the need for funds to operate and maintain these facilities that they're constructing. So alternatively, we can evaluate what we call the TMDL approach. TMDL is the total maximum daily load and represents the maximum amount of a pollutant that's allowed to enter a water body. So from a restoration perspective, this means treating discharges so they meet a TMDL standard for the overall watershed instead of at individual discharges. Most fundamentally, this requires you to identify all pollutant sources, both non-point and point sources. And the most significant challenge to this approach is that it is outside the existing MPDS permitting structure. Because of that, you have to document some type of cost benefit if you wanted to justify this approach. The jurisdictional questions we discussed earlier can present challenges, especially when it comes to determining who pays for treatment. Initial capital costs are higher, but long-term operational costs are lower. And this approach could restore more miles of stream than the point source approach because it does account for all the sources. And then finally, there may be some potential revenue benefit if we incorporate rare earth recovery to this approach. I'll touch on that a bit later, and Eliza will discuss that process in detail in her presentation. Based on analyzing these alternatives, we've identified what we call watershed scale restoration as our preferred solution, and this uses the TMDL approach. The process is outlined here. First, you characterize the watershed. That involves identifying all the sources, quantifying their impairment and potential benefit. Particularly, you need to know where loads that are contributing to a TMDL are coming from. From these data, you can develop a conceptual design with treatment alternatives to achieve your load reduction goal. Then you can estimate cost and revenue. Once this is done for multiple watersheds, you can evaluate watersheds by comparing criteria related to restoration, cost, and feasibility. At that point, you can allocate funding and determine appropriate long-term funding options and design and build the facilities. Next, I'd like to provide some basics on a case study in watershed scale restoration, the Muddy Creek watershed. Like I said, Greg will discuss most of what I'm talking about here in more detail in his presentation. So before the watershed approach in Muddy Creek, the only regulated discharges were permitted discharges at special rec sites and active operations. The AML discharges were present but not regulated. There were individual treatment systems operated at multiple special rec sites. Even with the existing treatments, Muddy Creek was severely impaired and accounted for approximately 50% of the acid load to the Cheat River. The treatment sites were expensive to operate and weren't restoring the streams. So this graph presents the distribution of acid load from different sources in Muddy Creek. As you can see, the vast majority of the load comes from pre-law AML sites. However, under the previous restoration plan, only the small fraction you see in blue, the regulated discharges were actually treated. So to address this, DEP designed and constructed the TNT AMD treatment plant. Instead of treating individual discharges, the plant consolidated AMD from multiple sources by conveying those to a centralized location. So in order to do this outside of the MPDS permitting structure, the EPA granted DEP specific in-stream variants for this site, and Greg will discuss details of the plant operation in his presentation. Compared to the point source approach, the centralized treatment facility had a higher capital cost but lower operational cost. Because DEP documented how successful it could be throughout the process, it also garnered contributions from Southwestern Energy, and that benefited the financials. On a 10-year basis, the watershed scale approach is slightly less than the point sources approach and significantly less if you include the contribution from Southwestern Energy. And Greg, again, will discuss those financials in more detail in his presentation. From a restoration perspective, benefits since the treatment plant went online have been seen in major metals, pH, and biological indicators. The graphs here present some comparisons of those things at the mouth of Muddy Creek, and these can all be reviewed in more detail in the Watershed Assessment Branch report for Muddy Creek. And then finally, we always like to show this before and after photo of the mouth of Muddy Creek into the Cheat River, just as a visual demonstration of the effectiveness of the treatment plan. Final thing I'd like to do today is share some of the current efforts going on here at WRI with respect to watershed scale restoration. So in 2023, we began a project with the West Virginia DEP AML program to investigate watershed scale restoration for watersheds impacted by AMD from AML sites. This was possible through funding in the bipartisan infrastructure law, or BIL. This provides funding to DEP not only for capital investment in the plants, but also long-term operation and maintenance, which will allow them to construct and operate AMD treatment sites throughout the state. In the first phase of the project, WRI has been tasked with characterizing and prioritizing watersheds that would use this approach. One important thing I'd like to note is we're not doing this in a vacuum. We're collaborating with multiple state and federal agencies and interested watershed stakeholders. The 4 steps I just described earlier are shown again here, so I'm going to touch in more detail on some of our current efforts in characterizing and evaluating watersheds. First step is characterizing the watersheds. So first we conduct broad sampling to identify all the sources and quantify their impairment. If broad sampling indicates a watershed should be investigated further, then we do more detailed sampling on individual sources. In this project specifically, it's important to know how much of the pollutant load comes from AML sites versus non-AML sites, since it is an AML project. Detailed sampling can also quantify the rare earth recovery potential of the watershed. And from those 2 pieces of information, you could determine how much you need to reduce the load to meet your goal and how much revenue the plant could have. One other thing is this step will involve working with watershed groups to help out with the sampling in addition to the efforts we have internally here at WRI. Specific thing I'd like to talk about is the cost estimate. So we'll want to know the cost for any of these potential projects. On the cost side, we can determine that based off the impairments we determine in our sampling efforts. And those are going to be dependent on what treatment strategy we use and how complex the design is. So for example, how many sources you have, and how easy or not it would be to get those sources to a centralized location. On the revenue side, that's based off the rare earth recovery potential. That's also based off the sampling, and then it's dependent on the current value of rare earths and the recovery technology. The recovery technology is a separate major research area here at WRI that's happening concurrent to this project. And Eliza will talk about that in detail in her presentation. One important thing I'd like to make clear is that rare earth recovery may or may not be included at any of these sites. Rare earth recovery is a potential benefit to treating AMD. It can provide some offsets to the cost, but lack of rare earth recovery would not preclude a watershed from being included in this plan. The ultimate goal and priority is restoration. So as we characterize watersheds, we're also developing tools for evaluating them. In the end, we'll have multiple watersheds that could be good candidates for this approach, and we'll have to determine which ones to work in. So for now, we've broken it into the evaluation into 3 major categories: implementation, financial, and environmental. Within those, there's subcategories. Within the subcategories, there's individual criteria. So I've just included a couple criteria for each category here, but we're working on a more comprehensive list. Individual criteria will be given weights based off our professional judgment and feedback from decision makers and stakeholders. And then those weighted criteria are what will ultimately be used to rank and prioritize watersheds. So this tool can be a living tool. It can evolve over time as priorities change. With that, I'd like to open it up to any questions you guys have. I'd also like to say that if you have any questions after this about our ongoing efforts or interested in becoming involved, I've had my contact info here. I'm just one member of a large team working on this, but I can be sure to put you in contact with the appropriate person if I need to. And thank you all for your time.
Thank you so much, Nate. That was a really great overview. We do not currently have any questions in the chat. So I think we can have you go ahead and end your screen share. Okay. And next up, we've got Greg Phillips.
Yeah, thanks, Nate, again. The next presentation will be given by Greg Phillips. Greg is an Environmental Resource Program Manager with the West Virginia Office of Special Reclamation. And as mentioned, his presentation is really going to be all about the TNT facility in Muddy Creek.
Okay, thanks so much for having me. Let me get, I have got my, let's see. Well, I have a little bit of trouble with Zoom because the menu is covering up my, let's see here. Let me do this. Let me stop share here real quick because it's at the top. Bring this up. I apologize. Exit full screen. Go here. Go there. And now I can't see. Doggone it. Try this again. I hate to give it like this, but I may have to.
Greg, I think you might be able to move the Zoom menu.
There we go.
Drag it.
Perfect.
My problem is I'm 54 years old, so. Anyway, okay, without further ado, I'm Greg Phillips with West Virginia Department of Environmental Protection. Been here for 21 years, and I'm going to go over a pretty modest detail, the Muddy Creek Restoration Project. Now, let's see here. There we go. Now, precisely where is Muddy Creek? Well, here's West Virginia, and you can see the Cheat watershed there outlined in green. There's Morgantown, and just east of Morgantown in Preston County, just south of Brewston's Mills off of I-68, you will find the Cheat watershed. It consists of course, Muddy Creek itself. And if you note there, the northern part of Muddy Creek, this is back in 2016. Let's move this. There we go. Back in 2016 was actually a trout stream. It is this, from the middle part of Muddy Creek down to the mouth, it was impaired by, there we go, Figgy Run, Glade Run, and Martin Creek. And to give you the lay of the land, here are the TNT portals, so you know approximately where all I'm talking about. Now, the Muddy Creek watershed, this was in 2017. We actually turned on, if you will, our TNT water treatment plant in December of 2017. But this is with the confluence of Muddy Creek, which here to the right, or pardon me, to the left was a trout stream. You can see no staining on the rocks here to the left. The shade distorts it a bit, but nevertheless, you can see the iron staining there on the creek coming from Martin Creek. And as you see further down the stream in Muddy Creek, you can actually see where the metals are falling out, where the sludge is forming. Now, Nate talked about the difference between Title IV and Title V discharges. And, you know, off of the Special Reclamation, we manage, and our purview is over the Title V discharges only. And we are required, as Nate alluded to, we are required to get an NPDES permit for each one of our discharges. And I want to go over the costs, and it's very significant when we're talking about a point source approach versus the advantages of going a watershed approach. The costs are one of the major keys. In 2016, we had determined that we would have to put or construct a brand new water treatment plant for the TNT mine, which was the main Title V contributor of acid mine drainage to the Cheat watershed. And from 1994 to 2016, we had spent $9 million of special reclamation funding in treating water. And with the new plant, we were going to spend another $8 million in capital costs to completely redo the TNT plant to meet our NPDES requirements. In addition, in 2016, we had 6 active water treatment sites within the watershed. Those had cost us $8 million to install. And we had spent over $3.5 million in operational costs on those sites since they were installed at a cost of about $50,000 per year. At that time, OSR had 3 additional sites that we had to construct at a cost of nearly $4 million in capital cost, and those would have cost an additional $120,000 a year in operation and maintenance. Okay. Is there anybody who could help me out with this and try to get rid of this? I apologize here, because this is really, oh well, I'll continue. Our capital costs were $12.5 million in total for all the capital costs that we would need to construct, and our total operation maintenance costs will cost us over $1 million per year. Now, as far as what all goes into a water treatment plant, you have your initial capital costs, design and engineering, dosing units to actually store and house the alkaline material you're putting in the stream, the settling ponds, the clarifiers, which allow for the sludge to form and go to the bottom of the ponds. And also you have computer monitoring systems that you have to put into these sites. Power, you have to run power to these sites, and also with a generator backup, because they have to run 24/7. You also have sludge storage, pumps, lift stations, because oftentimes the seeps, when they come out of the ground, you need to actually convey them to another location where you can actually construct the infrastructure to treat the water. A&D collection lines, road access, and the road access to these sites, oftentimes they're in very rural areas. You have to put a fairly robust access roads in, so you can get 18-wheelers, so you can not only service it, but you can also bring in your chemical deliveries too, and those are typically on 18-wheel trucks. Realty, oftentimes you have to go to landowners and you have to compensate them for the use of their land and go through the exercise of executing land agreements, compensate them for an easement, or sometimes flat out purchasing the land. And then you have, of course, your operation and maintenance costs. Those can be can include chemical deliveries, sludge disposal, which is a significant cost. And of course, the maintenance of these sites is also a significant cost as well, and the operators themselves. And keep in mind, on a point source approach, every single site we were doing this on, that's where the significant costs come from. Because not only you have your capital costs, you also have your operation and maintenance costs on all of these sites. So when you compare a watershed approach versus a point source approach, if we were just to treat the Title V discharges and what I just went over, okay, with the $8 million TNT plant, the additional 3 sites that we had to put in, we would spend $12.5 million installing those. And with all of those sites, the 6 we had, the 3 we were going to install, and the TNT plant, we would be spending approximately $1 million a year on operation and maintenance costs. And as Nate alluded to, because there was so much acid load coming from the Title IV discharges, this does not address the Title IV discharges at all. And Muddy Creek would still be a dead stream despite spending those kind of dollars. Now, if we were determined and we looked at this, to treat both Title IV and Title V discharges in a watershed approach, our capital cost would be $15.9 million. our operation and maintenance cost would be $530,000. Now you may ask, okay, what's the difference between the $1 million and the $530,000? Well, you're not putting in all of these sites at a point source. You're only putting in approximately 4 or 5 sites, not 8 or 10. You're only treating 5 sites. So your operation and maintenance costs go down. Now, in this, as Nate alluded to, we had a partner come in, Southwest Energy. They contributed, or pardon me, they have a freshwater neutral approach. And what their goal is, a company policy, they're not obligated by laws or anything else, it's their company policy. They have a freshwater neutral approach. For every gallon of water they use, they want to clean a gallon of water. So they partnered with us and gave us $2.5 million towards our capital costs and an annual contribution of $350,000 towards our operation and maintenance costs, which gave us a capital cost for this project of $13.4 million and reduced our operation and maintenance costs down to $180,000 per year. Now, the variance. I'm not going to get too deep in the weeds on this, but we just could not, for lack of a better word, wake up one day and go, hey, let's do a watershed-based approach. OSR had to coordinate with the EPA and actually change state code to meet the variance that we were going to essentially get our NPDES variance for an in-stream watershed-based approach. This was the first one in the nation. And the EPA helped us author this legislation, and it went through our legislator, signed by the governor. Once when that was achieved, the EPA approved that variance in August of 2017. And our NPDES variance is right there, just below, just at the confluence of Martin Creek and Muddy Creek. And you can see where the manhole is there, and we've actually had to alter the stream a little bit, so we've got flows during low flow, so we can take those samples. Now, the components of the plant itself. This approach would intercept approximately 86% of the acid load from Ficky Run, both Title IV and Title V discharges. 68% of the load would be reduction from pre-law mining. All of that, what Nate showed in that pie chart we were looking at. So all in all, we had a Glade Run in-stream doser. This addressed the contributors that we were not taking to the TNT plant. This is sort of a hybrid approach, the Muddy Creek project. We have both in-stream and we have where we're taking point sources, show that in a moment, to our TNT plant and treating them. So it's a sort of hybrid point source project. We also, here's the Title IV Liston mine. This was at the top of the pipeline. It actually took it to the TNT plant. It was a Title IV contributor of AMD to Muddy Creek, or pardon me, excuse me, Ficky Run. We had a Drop Lagoon Inlet, again, along Ficky Run, Title IV discharge. We had a Title V discharge. That was one of our current 6 plants where we were treating water at a Viking. And then we had a Pressed Energy Seep. This was one of the ones that we were to construct, but we put it into the pipeline here and took it to TNT plant to treat. And then we had to have a lift station as well. This is just down from Dream Mountain. If you're going up 26, right before you get to Dream Mountain, it's right there on your left. We had to pump the water up and over the mountain there. And all in all, we installed 2.5 miles of pipeline and, of course, took that all to the water treatment plant. As far as the plant itself, we have a lime slurry injection system, and you can see the lime slurry tank there to the left. And the best way I can describe lime slurry is it's water mixed with lime. And what it does is it's a little bit gritty and it's kind of very, very thin, but it's sort of like, it feels like a toothpaste, but that is injected into the acid mine drains to bring the pH up so the metals can drop out. In addition, we also put polymer in. And what the polymer does is it allows for the flock. As the metals drop out, it puts electrical charge on them and makes them connect with one another much better and forms, the best way I can describe it, it looks like a snowflake. And the snowflake gets larger and larger, and the larger that snowflake is, the more compact it is, the quicker it falls down into the clarifier, in this case, or the ponds, whichever we're using. That all goes to a mixed tank. Then we also have two 80-foot diameter clarifiers. And if you notice there in the middle where it's brown, that's where the AMD initially goes in. And that central cylinder goes down approximately a half to 2/3 down to the lower part of the, I believe it's a 25-foot clarifier. And the sludge settles to the bottom, and then the clean water, and then comes to the top and discharges through the weirs there as you can see in the clear area of the water. We also have sludge pumps, and we have two methodologies to get rid of the sludge, or two places we're putting the sludge. One, we're injecting it back into the mine. The other, we have geotubes, and we started using these several years ago, and they're very interesting technology. They have micropores in them. And what it allows once when you pump in the geotube bags and the flock is formed, polymer also facilitates the flock staying together once when it goes through the pump, or you'll get flock shearing, which when flock shearing occurs, it basically is that it's busting up the flock, and that polymer keeps it together when it goes through the pump. At any rate, what happens is when it goes into a geotube bag, that flock stays in the bag and the water discharges. So you can store the sludge that way as well. The geotubes here are more of a backup. We want to essentially put it all back into the mine. And then, of course, you have the discharge there along Muddy Creek there at the bottom. Now, one thing, Nate had given some benthic studies. This is actually kind of hot off the presses of the Watershed Assessment Branch for DEP. They had the 2023 data, and they should have their complete report out any day now, but they were nice enough to provide this for me. But here's the fish community population. So you can see there in 2015, no fish at the mouth of Muddy Creek. This is right before it enters the Cheat River. 2019 and 2021 through 2023, we're seeing fairly consistent fish populations return to the area where there were none previously. Now, a little bit of what we've learned. and Nate alluded to some of the work that AML had done. And we started, AML actually took the lead in the watershed-based approach on Three Forks and a couple other streams. And we have essentially two types of lime. We have pelletized lime. Now, the pelletized lime is kind of like a pea, and it drops through the silo very well. And you can introduce it to the stream or introduce it to the AMD fairly well through Aquafix units. But and we store all of our lime into a very large silo, and this falls through the silo very well. It is 98% calcium oxide, so it has a lot of alkalinity in it that reacts with the AMD and gets the pH where we need it. The problem is with pelletized lime, mostly the outer microns of the particle only react with the AMD. And the problem is you have a lot of unused lime when you're using pelletized lime. And the other thing, when you're going to when you're treating in stream and you're dropping the lime physically into the water, what happens is the lime has a tendency to kind of settle in a little eddies and a little where the flow is not quite so, is not so vigorous, and it kind of sits there. And what happens with pelletized lime, when you have a very high flow event, it starts it can bust up that lime, that pelletized lime, and now you have a quick release of that lime into the stream, and the pHs can fluctuate a little bit, which is not what we're looking for. So what we've moved to is hydrated lime. AML is now using hydrated lime. The trick with hydrated lime, you have to have a vibrator in order to drop it through the doser. And so that allows it to drop, and it doesn't rat hole, okay, if you will. And it gets on, and you can put it in the water and through the dosing it very well. It mixes very well with water. There's not a whole lot of unused lime with it. It's 71% calcium oxide. So its acid reacting capabilities to bring the pH up is not nearly as much as this in pelletized lime. And it's a powdery substance. It's sort of a sandy, gritty type of lime. Now, what we are using in our TNT plants, and we are moving to in just about all of our plants, is called a tech grade lime. Yes, several advantages. Now, you do have to put a vibrator on the dosing unit in order to get fall through the into the silo and then eventually to the mix tank and then mix it with water. You can't use it to drop directly into the AMD. It really needs to go into mix with water and form a lime slurry. It's just far too powdery. It'll blow around. So you have to really keep it contained and then mix it in with the mix tank. Now, due to the small mesh size, it works very well with mixing with water and forming that lime slurry, and it goes through the pumps very well. And it's 95% calcium oxide. And it's also, talking to Dr. Sienkiewicz and going into the rare earth extraction, it gives us a very consistent pH because it's very critical to have that pH very close to exactly what needs to be in order for rare earth extractions to occur successfully. So that's why this is one of the other huge advantages we have with tech grade line. And that's what we are actually injecting into our streams and into our clarifiers, and we're using it. The big thing with tech grade versus hydrated is if you look at the neutralizing capabilities, the calcium carbonate equivalent, if you will, you have 95% versus 71%. In order to neutralize essentially the same amount of acid mine drainage, I need less tech grade lime than I do hydrated. And it's the same price, at least the bids that we've had on the last two contracts. The difference between what I'm paying for per ton of hydrated lime is the same as tech grade. So there is a savings there. So anyway, a little bit of what we have learned. So that's all that I had, and I just wanted to see if anyone had any questions.
Yeah, there is a question in the chat. Why is it called watershed restoration and not big stream restoration?
Fixed stream restoration, is that what it was?
Big stream.
Oh, big stream? I'm sorry.
Yes, that's correct.
Oh,
Big stream.
I don't know. I've got into a lot of discussions about exactly how we would classify this, of how it would be. You know, one of the discussions I've had is okay, well, is it true restoration? Is it back to where it was? At what level do you get into restoration? You know, what can you define what restored is? So you're getting into a bit of you know, discussions of what of exactly what to call it. So, and what level is it be till you really achieve restoration? So, you know, it's sort of I guess where that nomenclature has gotten in with it's a watershed-based approach, so you're cleaning up the entire watershed. So there may be better verbiage for it since this is sort of the you know, this and our Left Fork Little Sandy project are the only two that I know that are currently, at least on this scale, and definitely on an NPDES approach nationwide. These are the first two. So there probably may be better definitions that maybe perhaps you could use. However, you can see that definitely the success in twofold. One, we have essentially brought back both in benthics fish populations to Muddy Creek that have not been there for a couple generations. And we have also saved, we've saved money in doing, and we're not wasting money doing something that actually is not getting anything done. You know, what we were just simply treating Title V discharges is just not an efficient use of the money that we have in order to spend. So that's about the best way I can address that one.
Greg, could I add something? So one way it could be seen as like a big stream recovery is, say, if you have all these sources that are impacted tributaries that feed to a larger stream, the stream and the tributaries are impacted and you're treating on the larger stream, then, you know, you're restoring the stream downstream of where the plant is, right? The one of the objectives with the watershed approach is not just that we're treating those discharges by allowing them to get to the point where they all contribute together. It's that we are getting the sources from the location they're at, taking those to a centralized treatment and treating them there. So the goal the big goal would be not just to recover streams downstream of the plant, but also restore the tributaries that contribute to that larger stream.
All right, one more question. Is there consideration for the nomenclature of managed watershed as opposed to restored watershed? Pennsylvania is taking this approach so as to alert people that without these systems, the water would not be cleaner. Also, any thoughts for a maelstrom oxidizer on the plant, or is there no need for CO2 off-gassing?
Yeah, right now we are doing pretty well at on the plant for what we have in place. The off-gassing is really not needed. We're meeting the limits that, because we have an NPDES discharge. We have an NPS permit on the discharge. So not only are we treating there at the Martin Creek variance, we are also have well, not only do we have an NPDES there at the Martin Creek variance, but we also have ones at T&T plant discharge. So right now, what we have in place, we're in pretty good shape. Now, what was the first part of that question?
That was on the, is there consideration for the nomenclature of managed watershed as opposed to restored watershed?
That might be more towards mine.
Yeah.
Presentation, Greg, the approach in general. So, the short answer is we acknowledge up front that in order to prove this is like a valid approach to use, we are going to have to document in some way how this approach would restore the watershed, right? So we are open to, input from experts or, using past success stories of how to do something to document what that looks like. So I appreciate you mentioning that. And that's something we can, talk about when we talk about what our kind of restoration criteria outcomes are. And we know we have to be very deliberate with the words we use when we are talking about the condition of a watershed before and after these treatment systems go online.
Perfect. Thank you both so much. Greg, you can go ahead and end screen share.
Okay.
And then Rachel.
Yeah, if there are no other questions for Greg, thank you, Greg. Our next presentation and final one will be given by Eliza Siefert. Eliza's a water resources technician here at the Water Research Institute, and her presentation will focus on rare earth, element, and critical material extraction from AMD.
Hello, let me figure out my screen sharing really quick. Okay, so is everyone seeing like the correct screen without all the speaker notes?
Yes.
Okay, perfect. So yeah, I'm going to be giving a presentation on rare earth element and critical material from recovery from acid mine drainage, or as I like to call it, recycling. Okay, so just a little bit about me. My name's Eliza Siefert. I'm the critical materials water researcher here at the West Virginia Water Research Institute. I'm originally from Parkersburg, West Virginia. I grew up right along the Ohio River. I have a Bachelor of Science in Environmental Microbiology from West Virginia University, and I've been working for the Water Research Institute since 2021. So my day-to-day, I support data analysis, laboratory, and field needs for both our waters, so AMD remediation projects, and then critical material projects as well. So with this research, we have some other groups and entities involved. I'm not going to read all of them, but notably there's Department of Energy, West Virginia Department of Environmental Protection, Virginia Tech's been a great research help, and then we've worked with Rockwell Automation, Solmax Geosynthetics, and then Montana Resources as well through this research. So I'm pretty sure you guys are all very familiar with acid mine drainage, but I'm just going to give a little bit of background just in case there's anyone who's not as familiar. So acid mine drainage forms essentially when pyrite-rich geology is exposed to air and water, typically during mining operations. And so then that pyrite oxidizes with the air and water and it forms sulfuric acid. And so sulfuric acid, it has a very low pH. Typically this reaction is exothermic, so it generates a lot of heat. And in turn, it leaches a lot of heavy metals. Typically you think of iron where you see like the yellow boy there on the right, but a lot of other metals are leached in the process. So there are over 12,000 miles of streams and rivers in the United States that are affected by AMD. And then there are 2,500 stream miles impacted by AMD in West Virginia alone. But AMD is not a US issue. It's not an Appalachian issue. It is a worldwide issue. There's AMD all over the world, and treatment for this can be very costly. Okay, so now a little bit about rare earth elements. You'll probably see them denoted as Re, just for simplicity. So rare earth elements, when you think of the periodic table, they're the lanthanides. So they're the block that sit right underneath, and it's just the top row. And then we include scandium and yttrium in there as well, even though they aren't technically lanthanides. So rare earth elements, they're used in catalysts, cars, cell phones, majority of the technology today. There's a large demand for them, but not a huge supply. If you've had your catalytic converter stolen, like I have, you know exactly how expensive they can be. So currently most of the world's rare earth elements are mined in China, and it's a very extensive and environmentally harmful practice to mine them. There's no good US supply chain of rare earth elements. So in 2016, the Water Research Institute found that rare earth elements exist in raw coal mine drainage across 140 separate sites. They aren't necessarily found in the same concentrations, but rare earth elements are consistently found within the AMD. And then cobalt and nickel, which are considered critical materials, they are found to be in a 1-to-1 ratio with the Re concentration in AMD. So just a little bit of a timeline. In 2015, the Department of Energy released a funding opportunity announcement to find rare earth elements in unconventional sources. And this is when we discovered that there were rare earth elements in AMD. 2017, we developed a 2-stage AMD treatment. So it treats the AMD and then also generates a rare earth element feedstock. I'll get into that a little bit more in the next slide. So 2018 and through 2020 was just our benchtop testing and design. It was very small scale. And then 2020, when COVID hit, it was the perfect time for us to scale up. So currently we do have a rare earth element recovery pilot plant co-located within an acid mine drainage treatment plant in Mount Storm, West Virginia. It treats roughly 500 gallon per minute AMD, and it's in conjunction with the West Virginia Department of Environmental Protection. And then, so that was the AMD treatment was fully online September 2022. And then we were producing rare earth oxides March 2023. And now currently we're evaluating other sources for possible watershed restoration, as Nate mentioned, and also rare earth element recovery. So like I said, we developed this 2-step AMD treatment, and this gives us our rare earth element pre-concentrate. So through this process, roughly 1 ton of traditional acid mine drainage sludge will turn into a 1/2 ton of sludge. And then that other 1/2 ton is our rare earth element feedstock or pre-concentrate that we use for further processing. And so I may use feedstock, pre-concentrate, or HPC interchangeably. If it ever gets confusing, just let me know and I can stick to one of the words. So roughly the same amount of lime is also used in this process as in used within traditional AMD treatment. Some sites do have a little bit of exception just based on the elemental concentrations of the influent AMD. So just to walk through this little diagram, the AMD flows into the first mixer and the first clarifiers, and lime is added and raised the AMD to a specific pH. That pH drops out, mainly it's iron and aluminum that drops out, and it goes to in-mine disposal or geotubes, whatever the current method is for AMD sludge disposal on site. Then that, then that water again goes into another mixer and clarifier. And again, it is raised to another pH with lime. And then that water is now treated. And then the solids that precipitate out is our rare earth element feedstock, or our HPC. So our HPC, or our feedstock, can be processed either as a slurry, which you can kind of see down here in the beaker, or you can pump it to geotubes and we can passively dewater it. And this allows the HPC to be stored if it needs time for storage, or it allows for transport. So we worked with Solmax Geosynthetics to develop like an optimal geosynthetic fabric to work for rare earth element capture. So the slurry right here in the beaker will get pumped to the geotube there on the right. And then it is passively dewatered and we're yielded a solid product similar to what you see there in the middle. But either way, you process the HPC the same, whether or not it is a slurry or a solid. So the HPC undergoes acid leaching and then solvent extraction. So essentially at each step, the rare earth elements get more and more concentrated into smaller and smaller volumes. So essentially at the end, you're left with this organic solvent that's very rich in rare earth elements, and we acid strip that solvent, and that gives us our rare earths. And then we further purify these rare earths to give us our light rare earth oxide and our heavy rare earth oxide. And so these oxides are the marketable form of the material. So like I said, we do have a pilot plant outside Mount Storm, West Virginia. So this is an automated system capable of being remotely monitored. We are currently producing heavy and light rare earth oxides at purities greater than 90%. There's a little photo of some of them below. The light is on the left and is like more of the purpley pink. And then the heavy rare earths are on the right and they're more of a yellow brown color. And so this plant has the ability to produce 1.7 metric tons of mixed rare earth oxides per year with the 500 gallon per minute inflow rate. So currently, our final report of the project is in Department of Energy review, and we have plans to make it publicly available once it's all gone through that process. We do have plans for a central refinery, so the rare earth enriched pre-concentrate, or the HPC, would be transported to a centralized processing facility. So that means only lime would be needed on the AMD treatment site, and then all other processing would occur at a centralized facility. And so this is where the geotubes that we developed come into play, because it allows for the HPC to be dewatered enough to allow for transport. And so overall, our goal is to restore AMD impacted watersheds while recovering rare earth elements and critical materials, and then utilize that money that's generated to cover plant operation and maintenance. So our program goals, overall, we want to incentivize AMD treatment. We just want to encourage more landowners and operators to treat. And in turn, we're just going to restore more watersheds and streams. And we want to be able to provide cost savings to reduce operation and maintenance costs so that this is more feasible. We also want to create additional jobs for economies that are currently dependent on coal. And overall, we want to develop an independent rare earth supply chain in the United States so we don't have to rely on very extractive industries, how we currently get our rare earth elements. So I know when I started, I had a lot of questions. So I'm hoping my little FAQ section will help answer some of the ones you may have as well. But again, there are time for questions at the end. So first off, who gets the benefit of rare earth element recovery from acid mine drainage? Long story short, those who treat the acid mine drainage get the money. So in the West Virginia State Legislature, House Bill 4003 was enacted in 2022, and it states that the entity that's responsible for treating the acid mine drainage gets the economic benefit from any byproducts. So for the case of the West Virginia Department of Environmental Protection, any of the money would go to their funds to cover operation and maintenance for their treatment systems. Is rare earth element recovery environmentally beneficial? The short answer is yes, but I'll give you the long answer. So overall, our goal is clean rivers and streams. We wouldn't be doing this if there was any risk of polluting anything any further. So our process is environmentally benign. Nothing exits our systems. We have conductivity controls, pH controls, and numerous check valves. So nothing can flow anywhere that it's not supposed to. If a conductivity probe says that something is at a conductivity of 0, the system shuts off and all the valves close. Nothing's going anywhere. All of the extractants that we used are recycled, so that cuts down on cost and cuts down on risk of them exiting the system. And then, like I said, we do have plans for a central refinery, so only lime would actually be needed on the acid mine drainage treatment site, and all other processing would occur in a centralized facility, reducing any risks. So the upstream process where we create the HPC or the pre-concentrate is the same as conventional AMD treatment. It utilizes lime, which is used in both passive and active acid mine drainage treatment systems. The downstream process, where we recover rare earth elements from the pre-concentrate, does not generate any hazardous byproducts. We have done toxic characteristic leaching procedure, or TCLP testing, and all of the hazardous materials that tested for came back at acceptable levels. So that includes arsenic, barium, cadmium, chromium, lead, selenium, and silver. We monitor thorium and uranium with every sample we have analyzed, and they always come back at acceptable levels. And then we have had our products tested for gamma, beta, and alpha radiation, and it's not a concern, even with like hard rock acid mine drainage. In fact, the people who tested it for us told us we could roll around in it if we wanted to. And then the only offsite discharge is the effluent water, which is treated to NPDES compliance. Another question is, will rare earth element recovery promote additional mining? Short story, no. But again, I'll go into the long answer. So rare earth elements are only recovered from acid mine drainage during treatment. No rare earth elements can be recovered through traditional mining methods effectively, especially in the United States and Appalachia. Rare earth recovery just barely offsets operation and maintenance costs. The revenue that is generated does not justify additional mining just to create acid mine drainage to extract rare earth elements from. The rare earth elements may pay for part of the treatment, but not much, if any, over. So for example, at our A34 site, the projected revenue just barely offsets the operation and maintenance costs for the treatment facility. And then we've done projections for other sites, and they're all very similar. And so we want to incentivize AMD treatment at abandoned mine lands. So the re-recovery would be the cost savings for reclamation. And again, that money would go into the West Virginia funds for operation and maintenance. We want to incentivize treatment through cost savings so that we can restore streams and again, develop this independent supply chain. And I just want to note again that the only byproduct from this process, besides the rare earth elements, is clean water. So looking forward, we are identifying additional acid mine drainage sources for treatment and rare earth recovery. Like Nate mentioned, we're looking to use bipartisan infrastructure law funding to restore abandoned mineland sites, and we're looking at watershed-scale restoration. And as Nate mentioned, some of those sites may justify rare earth recovery, but not all of them will justify rare earth recovery while we're doing this watershed-scale restoration. And again, we want to develop this independent US supply chain so that we can get rare earth elements from environmentally friendly practices instead of how they are currently being obtained. So yeah, I would like to open it up for questions, but I also have my email up there if you want to contact me privately. I will say some of this research is proprietary, so there may be some questions I may not be able to answer to the fullest, but feel free to reach out with me and we can always talk more and I can put you in contact with other people. Thanks.
Thanks, Eliza. We've got 2 questions in the chat. So
Okay.
first, are you finding all rare earth elements or some more than others?
Okay, so within the analyses, we are definitely finding about all of the rare earths that we analyze for, but the the most prevalent ones that we are finding in AMD are yttrium, lanthanum, cesium, and dysprosium. But lanthanum and cesium, they have a very low value. So yttrium and dysprosium are like the most economically viable ones that we are finding in the highest concentrations in AMD. And so how they vary from site to site, it is kind of pH dependent of the AMD. Typically, we find more rare earth elements present at a lower pH, but every site's different. So yeah, like we are doing right now with the watershed scale restoration, is doing all of this large scale sampling to be able to like create a map of which like watersheds and which coal seams are producing more rare earth elements within their acid mine drainage. Okay, so I see a few from Brandon. So feel free to email me for some of these. I may want to put you in contact with someone who's more on the techno-economic side than I am. But typically, the metric tons we're thinking are we want to produce at least a half of a metric ton per year. Again, this is current research that is ongoing, so it does, we are going to vary that number a little bit. And then the disposal of sludge, all of the rare earth sludge we utilize fully. Some of our intermediate byproducts, we are currently doing more research to see industrial and other uses that they have. But currently the like AMD sludge that's from the first pH cut, it goes to whatever disposal method is currently there on site. And yeah, we have looked at refuse piles as rare earth element source material, but right now we're currently focusing on discharges from abandoned mine lands.
Yeah, one thing I'll add on the rare earth like tonnages is there's a difference between how much rare earth you can extract from a site and whether that projection justifies creating a mixed rare earth oxide at that site or not. But it's more so, comprehensively, if we look at as many sites as possible as different feedstock sources, creating the pre-concentrate, how much of those can we produce to go to a more centralized location to recover the actual rare earths? So it's less, on a site-by-site basis what justifies it, and more on the network approach, how many sites do we need to justify the centralized location?
Yeah, just to add on to that, if like a source of AMD has a very high concentration of REEs, it doesn't necessarily always make sense to extract it, especially if it's a very low flow situation, because then like the loadings of the rare earths we're getting is not economically feasible.
Thanks,
I'm
everyone.
going back to your, will there be any coal mining trying to extract rare earths and not necessarily after the coal? I can't 100% assure you, but I can say this, we have plenty of sludge. Come get it. That's not going to be an issue.
Yeah.
So yeah, we're happy to partner with you on this, and the fact that it could conceivably fund our programs and do greater things for us and for the environment, and what it does for technology and our national defense and everything else is pretty doggone exciting to be involved with. And so yeah, I can assure, if we run out of sludge, holy moly, that would be amazing. So anyway.
Thank you, everyone, for attending, and thanks again to all of our speakers throughout the series. We'll be doing it again next year, so keep an eye out for the information. And Becca Phillips will be sending out a follow-up email to everyone with the recording and the slides, so look out for that as well.